Hello.
Good morning, everyone, and welcome to SIICaP webinar on imaging sensors. I am Dominic Vargas Jr. from the Space Data Mobilization and Applications Division, and I am one of your hosts for today.
I'm Chief Anne of the Space Data Mobilization and Applications Division, and I'll be joining Dom as one of your hosts. Welcome, everyone, to today's webinar. We have focused on the diverse initiatives driving the development of imaging sensors, systems, and their data processing pipelines. Throughout our session, we will delve into the sensor systems, their platform, operation, and process of data generation. With us, we are honored to have two distinguished guests, each bringing a wealth of experience in this field to enrich our discussion. By the culmination of our webinar, we aim to underscore the critical importance of leveraging the right sensor technology to ensure satellites are equipped for optimal performance. Let's embark on this enlightening journey together as we unravel the significance of imaging sensors in satellite technology.
Thank you, Keith, for the brief introduction to today's webinar. We would like to acknowledge our participants from various universities, colleges, local government units, and national government agencies. And just a few reminders for our audience. Please stay on mute if you have any questions, and please do not hesitate to drop them in the chat box. And rest assured, we'll present them on your behalf during the question and answer session. Second, Please be reminded that this session is being recorded and can be replayed on our YouTube channel. And finally, please accomplish our evaluation forms to receive your certificate.
And now, to officially start the program, Dr. Ariel C. Gamble, Director of the Space Information Infrastructure Bureau, will deliver his welcome remarks. Unfortunately, Dr. Ariel is on travel, but he has recorded this message.
Magandang hapon po sa ating lahat. Welcome to yet another exciting session of SIICaP webinar. The Space Information Capacity Building and Training Program, or SIICaP, aims to promote and enhance understanding of space information infrastructures and their applications through webinars, hackathons, workshops, and short courses. This is PhilSA's Space Information Infrastructure Bureau's way of disseminating information and knowledge, and eventually building and enhancing capacities through collaborative engagements. In the past SIICaP episodes, we featured talks and discussions on space data mobilization and on Philippine space exploration, which we called Lakbay Kalawakan. Satellites or the platforms we use and how they are put into orbit are important and interesting. Equally important and amazing are the payloads they carry. This afternoon, we are fortunate to have two inspiring and amazing women working in the forefront of imaging and their various applications. Dr. Therese, who is originally from UP Diliman, is with Australia's Commonwealth Scientific and Industrial Research Organization, or SIICaP, and Professor Dr. Maricor Soriano from the National Institute of Physics, UP Diliman. Ma'am Jing and Ma'am Therese, maraming salamat po sa pagpapaunlak sa amin. Sama-sama po tayong payamanin ang ating kaalaman at gamitin ang yamang kalawakan para sa isang mas magandang bukas. Magandang hapon pong muli sa ating lahat.
Thank you, Director Ariel, for your welcome remarks. As he said, sabay-sabay nating pagyamanin ng ating kaalaman patungo sa ating lakbay kalawakan. Now, I know that everyone is excited to hear our speakers for today's session. So without further ado, let me introduce our first speaker. Our first presenter for today is Dr. Therese Rollan. Dr. Therese Ann Rollan is a space technology research fellow at the Commonwealth Scientific and Industrial Research Organization in Adelaide, South Australia. Her presentation is titled High Altitude Pseudo Satellite Hyperspectral Data Cube. Dr. Rollan studied geodetic engineering and geoinformatics at the University of the Philippines, Diliman, and recently received her doctorate in computer science with a graduate certificate in research and innovation management at Swinburne University of Technology, Melbourne. From 2014 to 2017, she was part of the PhilLiDAR 2 program under the Agricultural Mapping Project, focusing on the research and development of processing workflows and training of partner universities and local government units. In 2018, she joined the I Am Blue SIICaP project, working on seagrass mapping and growth geosimulation. All the while, she was a college instructor at the UP Department of Geodetic Engineering, also in UP Diliman. Currently, she is a member of the CSIRO Space Optic team and oversees the development of spatial data processing pipeline for satellite and high-altitude pseudo-satellite Earth observation payloads. Good day, Dr. Therese. The floor is now yours.
Thank you. I'm now going to share my screen. Can you see my screen? And is my audio, can you hear me clearly?
Yes, Dr. Rollan, I think
Okay.
your screen is seen and you're audible.
Yeah. Okay, thank you. So thank you for having me today. My presentation is about high altitude pseudo satellite, or HAPS, Hyperspectral Data Cube. So maybe I'll just get an introduction about CSIRO. So we are Australia's national science agency and considered as one of the world's largest multidisciplinary science and technology organization. And across Australia, we have 51 sites with around 6,300 people working. And through the years, CSIRO has already invented lots of impactful produced inventions. I think I'm also surprised that the top one is a Wi-Fi. So CSIRO invented and patented wireless alien connection. Second is plastic banknotes. We also have Hendra vaccine, extended wear contact lenses, and AeroGuard insect repellent. So all of these inventions have interesting stories, which you can check out via csiro.au. And across CSIRO, we have different business units. Some are agriculture and food, space and astronomy, data 61, energy, but our team is under manufacturing. So all of these business units, they worked on various projects so that we can produce this multidisciplinary inventions. So for the space optics team, just an introduction of the people working with me. First, Stephen Gensomer is our team leader, and we also have Craig, Josh, and Eugene, who's working on the hardware and optical design. We also have Kenji and Rakitha. They are mainly working on quantum communications, while me and Miki, we are working on particularly HAPS. And also I am working on low orbit satellite. So here are the sensor payloads arranged based on the altitude. So the high altitude balloons or the pseudo satellites are in between drone and the low orbit satellite. So the altitude of these balloon payloads ranges from 25 to 35 kilometers. So for HAPS, we are these are the people particularly working on this project. Nikki for the operations and agricultural research, our team leader is project lead. So myself, I'm working on image and data processing. Joshua on optics design, calibration and image processing, Craig on optics and mechanical design, and Michael Salim on firmware and operations. So what is HAPS? So I think we are really more familiar with drones and satellites, and HAPS, if you will search it in related literatures, you will not really find that much information about it. It's fairly new. So in terms of altitude, as I've said a while ago, it's in between drones and satellites. And if we will compare balloons with these two, so I think mainly the difference are coverage area. So with drone, you have higher resolution, but low coverage. Satellites, you have high coverage, but relatively low resolution. But for balloons, I think the main advantages are it can cover relatively wide extent. At the same time, it can give you high resolution. And when compared to satellites in terms of costs, so balloon payloads are really very significantly low cost. So just to share with you typical configuration of a HAPS payload, we have the weather balloon on top, and it should also carry a parachute so that your payload can still be recovered and will not be that damaged when the balloon bursts. We also have a backup tracker so that you'll know where to find your payload afterwards. We also have a control camera. So control camera, it's just we only use GoPro. So for radar reflector and avionics, so you need this so that your payload can be detected by air traffic control. And of course, we have the gondola that carries your payload. So just very briefly describing how a hyperspectral image is created. So we have the scene on the left side, middle is the camera, and on the right side is our sensor. So in between our sensor and the camera, we have a slit or a gap. So once a light passes through this gap, we have a prism. So the prism is the one that disperses the light, the incident light. So that will have this continuous wavelength. And then once you have your hyperspectral image, you can do some corrections, and afterwards you can use your hyperspectral image for various applications. So each pixel will have this kind of graph, which depending on your feature, the response of the wavelengths will vary. So in terms of our project, we are mainly concerned on agricultural and water quality. So in terms of agriculture, perhaps we can use it for resource inventory, growth monitoring, crop pests and disease outbreak detection and control. So for example, on this side, we have a photo, a very good photo from a GoPro. It is captured from our flight in Clare Valley, South Australia. So you can, from the data that you gather, you have this image on the left side. And depending on your feature, usually your main classes will be vegetation, built up, water, soil. So you can have these varying responses based on the feature type. So you can use that for various different applications. On the right side, we also have for water quality, we've flown a payload in South Australia as well. So it is in collaboration with South Australia Waters. This graph shows plots of a pre and post algicide dosing. In this photo, you can see that before you treat the lake, in this example, you have this high values along the 550 nanometers and 700. So this shows the spike caused by the algal blooms as compared to after treatment of the water. In this plot, you have the yellow line. So you can now compare that after treating the water, the spike disappears also on this 700 nanometers. The other applications that we are looking at, natural disasters monitoring. So maybe in terms of Philippines, the main disaster will be typhoon, earthquake. But for Australia, the main natural disaster concern is bushfire. In terms of mineral exploration, you can also go with multispectral, but it will not be that detailed in terms of mineral composition. So you really have to have a hyperspectral image. We also have defense. In terms of defense, actually you can use it to detect missiles in the atmosphere because visually you can't really see a missile coming over to an area, but with the hyperspectral image, you can detect it by observing the difference in the atmosphere, like maybe the temperature and how the missile affects the atmosphere as it passes through it. Also, it can be used for environmental surveillance. So for me, I'm more concerned on the image processing. My objective is to develop a processing pipeline that will build a stitched, geometrically corrected, and georeference hyperspectral data cube. So since we are from manufacturing, we are on the development phase. We don't have data yet that we can process right away. That's why our objective is to create a hyperspectral data cube, which will later on be corrected and then applied for various different applications. We are not sure how familiar the audience is for remote sensing and photogrammetry, but I will just introduce the two. So for remote sensing, it is concerned with the observation analysis of Earth's surface and atmosphere as compared to photogrammetry, which is concerned with 2D or 3D measurements from photographs. Also, another difference is remote sensing is concerned with spectral data to understand various surface properties, while photogrammetry is more concerned on the geometric properties derived from photographic images. So from these differences, what are the similarities? So they're both concerned with aerial imagery, spatial data to extract meaningful information, GIS integration, and applications such as urban planning and disaster management. For our group, we are under manufacturing, so we have to build first the data cube. That's why we are concerned first with the photogrammetry, mainly on the photogrammetry. In terms of remote sensing, when we say pre-processing involves correcting for atmospheric effects, radiometric calibration. But for us, it's like pre-processing because the images that we get from our payload are like the very raw versions because you still have to stitch them together. You still have to correct them for geometric effects of the tilt of the camera and so on. Here are just some of the algorithms or the processes that we have to use in order to produce the hyperspectral data cube. First is the feature matching. Feature matching is the technique used to locate similar features between different images or within the same image, and it is essential in many computer vision tasks such as object recognition, image stitching, and 3D reconstruction. So for example, in these two photos, you have a very perspective or very tilted photo on the left side, and using feature matching, you can detect features and find those features that match on another image. Why is this essential for constructing a hyperspectral data cube? It's because we have different frames captured at different locations, and you want to have a more continuous image at the end. So how would you do that? So you use feature matching in order to overlay them together and to stitch them to have a continuous mosaic. Here is an example of the image stitching and from our one of our very first launch. We have on the left image are the features identified, but not all of those features can be used. It's because maybe those features cannot be detected to the other photo, or maybe it's because that it just can't find the corresponding feature. Sometimes you can also encounter features that are not correctly detected. So how do you filter those? So for us, we just use computer vision readily available Python packages wherein you can just specify some thresholds to filter those features. Here is an example of the frames stitched together progressively. Then after that, for your hyperspectral images, depending on the movement of the balloon, remember that balloons, you don't really have that capacity to navigate them. So it will really be dependent on weather conditions. So if you have very high speed wind, you can encounter these gaps. So on the original image on the left, you can see lots of gaps, even no data pixels. And how do you go about that? So you use image enhancement. Image enhancement is a set of techniques used in computer vision and image processing to improve visual appearance of an image or to convert the image to a more useful form of analysis and processing. So for instance, this one is filtering is a form of image enhancement wherein you fill in the gaps based on your surrounding pixels. So there are lots of filters that you can use. Maybe the most appropriate one for this example is a median filter because it's not affected by outlier values as compared to average. So you can use median filter to fill in the gaps calculated based on the surrounding pixels so that you can produce this image on the very right. So now you already have filled the no data pixels. But a more intelligent one is using AI, of course. So this one, in using AI, you make use of the context, not just the neighboring pixel, but it's like you're tracing a broken line, for example. For us humans, it's more intuitive, but when you're using it, you're teaching the computer how to do it, it is a more rigorous or more sophisticated technique. So I think for this one, more popular terminologies in painting or the process of reconstructing lost or deteriorated parts of images and videos. And the goal is to fill in the missing areas or remove unwanted objects in a visually plausible way. Another thing that you have to do in order to produce a usable hyperspectral data cube is georeferencing. So usually you access ground control points or you manually put them or assign geographic location into your image. And you do this by just manually picking the pixels and then assigning a coordinate system and latitude or longitude, for example. However, for our project, we are trying to eliminate the manual procedure. So I'm the one assigned to developing that. So with this novel approach, you eliminate the need for control point accessibility, logistics, and temporal variability, the need for online processing, the need for repetitive manual intervention, and prolonged processing duration. So just a day in the life of what I'm doing in the office and of course in fieldwork. So this is a photo of our payload. So for now it's encased in a styrofoam, and within this, as you can see, the size is fairly small alongside this laptop, right? And inside this, we have 2 cameras, we have the batteries, Raspberry Pi as its computer, and etc. This is just a photo from a GoPro from a previous flight and a video of the images that are captured from the payload. So my task is to create a contiguous mosaic. So it's like this jigsaw puzzle, and you identify which images are alongside each other so that you can create this big image. So for our imager, we have panchromatic imager. Spatial resolution is around 5 meters at 20 kilometers altitude. Field of view is 2.5 kilometers at the same altitude. With regards to the spectral imager, we have a range of 400 to 780 nanometers with a spectral resolution of 5 nanometers. And for this one, the pixel resolution is 8 meters at 20 kilometer altitude. So here's another video, but this one is, I think, the flight, with this flight, the wind is really fast. I even have to slow down the video so that you can see the features. So how do we construct the hyperspectral data cube? We have a spatial image. So you use the spatial image as a reference for when your slit is located. So what does the slit use for? So it represents a third dimension, which is your spectral image. So you have, for the 2D, you have like a latitude, longitude, while the third dimension is your varying wavelength. So here, just to share you guys the fieldwork that we had. So the first one is Auburn, South Australia. The payload info, we have a focal length of 75 millimeters. And so for the size of the camera, for the spatial, the image will be produced at 1100 by 968 pixels. For the spectral camera, we're producing 550 by 800 pixels. So Auburn is just around 2-hour drive from Adelaide City. Here is a photo of the payload with a balloon. So in this photo, we are being assisted by a company that launches balloons. This balloon actually is the smallest one. And with this small balloon, you have to have your payload within around 2 kilograms. So if you go over 2 kilograms, you have to use a bigger balloon. So this is the payload on the left side, and on the right side is a video of the launch. So when you're launching, you have to really check the weather. And when checking the weather, so this is the challenge, because even though you check it like 2 days before the flight, it can still change. And ideally, you want to launch before 10 a.m. because your target time range is 10 a.m. to 2 p.m. so that you don't have that huge effect by the sun angle. And ideally, you want to have a clear sky. So you can see this one. For this flight, we really have a clear sky, no clouds at all. For this particular flight, so here is the plot of when it went up the sky. This is where the balloon burst at around 30 kilometers. And then, as you can see, the moving speed is quite drastic. And in terms of temperature, so this is also another thing that you have to consider is the temperature, because if you go up really high, you can see that the temperature will go up to like negative 55 degrees Celsius. And then what's really good about this payload is you can use it again. So how do we retrieve the payload? We just use a free website. I think this is free. And then that's why you have those telemetry devices that can tell you where your payload is. And in this website, you can see real time how it will move, and it will also change based on the current weather conditions, like the direction of the wind, how fast the wind is. And then I think I have, this one is a video, and we're already trying to locate the balloon. So that's the balloon payload, and the orange one is the parachute. And then after that, when we retrieve it, we just plug in the hard drive and then download the data. Then you just have to check your the status of your camera. If it's still good, for this one, it's still good, we can still use it again for another flight. But the challenge is, for example, if you really have to capture images along river, so that's a challenge. It can still float, but you really have to pay attention to how you can make it waterproof. This one is sample of the stitching. You have on the left are the spatial images, and on the right side is the estimate locations of the spectral images based on the slits. So as you can see, this one is still going smoothly, and the path is not too crazy, but I'll show you another one which looks really crazy because you cannot really navigate the balloon. So it will just go around your area, but if you have the specific areas that you want to capture, currently we don't have that capability yet. And just to show you the spatial images footprint. So the yellow line is the path, and then since you don't have that capability also to adjust the attitude or the tilt of the payload, so you can get these frames wherein the boundary of the frames are already what do you call this, stretched because of the perspective effect. And another one we launched in the east of Adelaide because our target site is the Almond Center of Excellence orchard. So that orchard has this controlled plots of almond plantation. And from that, you can ask them for data for validation and calibration of your images. So just to show you the actual data cube, hyperspectral data cube. So on the left, we have the panchromatic image mosaic generated from the spatial frames. At the middle, we have the hyperspectral data cube in red, green, and blue composite, which is the true color composite. And you can really observe the slits and the effect of the movement of the balloon. So ideally, you would want a really, what do you call this? A calm movement, calm wind speed, so that you won't have these huge gaps. And on the right side is just a comparison of the images that we produced with Landsat 9. And this one is just to show you the coverage comparison. So because the hyperspectral images, we are only depending on the slit location. So it is expected that you have more coverage with regards to the panchromatic as compared to your hyperspectral. So at the bottom, we have the panchromatic overlaid with your corresponding spectral image. This one is a photo of Almond Center of Excellence. Because the payload, you can not navigate it. It can either skip your target site, and if you're lucky, you can go over it for lots of sweeps. And in terms of that, we are currently working on making that capability so that if you really have to have a data of your target site, you can certainly have or capture that area. Another example is this. So this one is not in South Australia. It was captured in Victoria, Horsham, Victoria. On the left side is your true color composite, while on the right side is your false color composite. So true color, as I've said a while ago, you're using the red, green, and blue bands, while on the right side you have a false color composite for particularly for the use of detecting vegetation. This one uses, instead of blue, it uses your near infrared, red, and green. So here, I can't zoom in, but if you can see this, where you have this track oval, then you have this green line and then also a green area here. But initially, you won't really notice that green area around beside the track oval is water. But if you use NIR red green for your false color, you can easily detect it just by seeing if the portion is showed in red or not. So if you will compare now these two portions, if you can see my cursor, the line here around the track oval, and then compared to the right, you have it is showed in red, so that is vegetation. But if we will see this portion here that looks green, which originally you can't really see whether it is really vegetation. Now using your false color, it is not red, so it's not a vegetation. It's actually water. It's marshed water. So what are the upgrades in progress? Because we are in manufacturing, our concern is to improve the payload first before we proceed with the actual application. So one of the upgrades are increasing the spatial coverage. We are developing a mirror that will scan it. And in that mirror, you can specify the amount of tilt and the speed of the scanning, so that if you have specific target site, you can specify where it is located using a GPS location, program it into your payload so that when you go over that area, like you can specify a certain radius, then you can tell your mirror to tilt it going that way so that you can make sure that you have data on your target site. The second one is capability to capture predetermined target study sites, which I've already mentioned a while ago. Custom wavelength range and resolution for various applications. This is also one of the most important upgrades because with various applications that you can't really practically make one single payload that will be used for all applications, because these features, the features that you want to observe, respond differently in various wavelength range. So you really have to have that capability to specify what wavelength range you have to use in order to capture your target features. Next one is the ability to capture for long durations. As you can see a while ago, as the balloon goes up in higher altitude, it seems like you're just waiting for it to burst, and then suddenly you just quickly go down. So with that, you can't really do some monitoring, and you can't really capture lots of data. So it's really important to be able to build this capability. And then in terms of processing, because you want to capture for long durations, your hardware allocation might be, for example, our flight is around 2 hours, 2 to 3 hours. With that 2 to 3 hours, you already have 500 gigabytes of data. So it's really huge sets of data. So you want to be able to reduce those data by doing some onboard processing. So this onboard processing is also crucial, very crucial. So I guess I'll just end my presentation with this very interesting, fantastic photo from our previous flight. So what do you think happened at this very moment? So at this very moment, you can see those white stuff going around. It's because it's when the balloon burst. So maybe we can compare it to achieving your dreams. So when you achieve your dreams, even though for this flight, you know that's gonna burst along some altitude, right? But you still want to go with it, even though it will burst, because what's important is the data that you will have after you recover your payload. That's also a journey when you're chasing your dreams. The important stuff are your experiences that you got and the learnings from it. So yeah, that's it. Thank you. Thank you so much.
Thank you, Dr. Therese, for leading us through the development of CSIRO Pseudo satellite and the hyperspectral latency group. I'd like to personally congrats Dr. Therese for this very interesting technology that we have being part of it. So, right, Tom?
Yes, that's great. And we will have our question and answer session later for our speakers presented. So if you have any questions for Dr. Therese, please type in your questions in the chat and we will read them out later in the question and answer session.
That's right, I know our audience have a lot of questions right now. We're actually seeing them. So please type in your questions using our chat box. Let us now proceed with our next presentation. Our second speaker today is Dr. Maricor Soriano, or Doc J. She will present local initiatives on developing hyperspectral camera. Dr. Maricor Soriano is a professor of physics at the UP Diliman, where she heads the video and image processing group. Her lab specializes in multidisciplinary research, which leads to the development of hardware and software tools for various imaging use cases. From 2018 to 2022, she led the Optical Technology In-Depth Knowledge Acquisition and Localization, or OPTIKAL, project, funded by the Department of Science and Technology. The project aimed to locally develop optical payloads for both air and space platforms. She will talk about HIPE, the drone-borne hyperspectral camera being developed for agricultural missions. Good day, Dr. Jane. The floor is yours.
Thank you. Could you give me a sharing capability, please? Because my share button is on gray.
Okay, Doc Jing, I think we're adding you as a presenter so that you can share your screen. Okay, just give us a few seconds. We're giving you the presentation role. Okay, while our team is currently fixing some technical issues, we would just like to remind everyone that if you have any questions for Dr. Therese and also Doc Jing's presentation later, you may leave them in the chat box. And later on, we're going to be reading them during the question and answer session. Currently, there are actually a lot of very interesting questions in our chat box. So if we have a little more time afterwards, we could also send the remaining questions to our speakers if that's okay for them to answer later. Okay, so I think we're currently giving the presentation role to Doc Jing.
What can we do?
Okay, I think we're having some difficulties on our end in giving the share access. Would it be okay to ask for a copy of the presentation so that we could?
Yes, absolutely. Hang on a minute,
Thank you
please.
so much.
Okay, to whom should I send the link? It's a Google slide.
Yes. You could send it to Mr. Nico Pante. I think he's here in the
Sorry about this. We tested it earlier.
And for our participants, we would just like to remind everyone that to please stay until the end of the event, and we will be giving an evaluation form for you to answer and accomplish in order for you to receive your certificates at the end of the workshop. Thank you very much.
I can now share. I
Okay,
already
okay, I
have
think that's
shared.
very great, Doc Ching. Okay, so the floor is now yours.
Can you confirm if you can see my slides?
Yes, Doc Jing, your slides are visible and your audio is clear.
Thank you. Good afternoon, everybody. Sorry about that delay. So I'm going to expand my discussion a little bit to include other payloads that we developed. So I slightly modified the title to Local Initiatives in Developing Optical Payloads. Hi, my name is Maricor Soriano, but you can call me Jing, Jing. That's my nickname. And I'm the project leader for the project OPTIKAL. OPTIKAL stands for Optical Payload Technology, In-Depth Knowledge Acquisition and Localization. And it ran from December 2018 to June 2022. So it ended 2 years ago, and we went and worked throughout the pandemic. The idea of this project, this is part of the Stamina for Space program, which is the successor to the Philippine Microsatellite project. The thing is, we developed the Diwata 1 and Diwata 2 satellites. Diwata 2 is still in space. And we also developed the Maya CubeSats. These satellites were developed together with our Japanese university partners. But what was not learned throughout the program was how to make the optical payloads. And so the optical project aimed to be that project that will try and learn how to make payloads for satellites, and particularly among these objectives, to collaborate and with local industries so that we can build a local space industry base. So essentially, we're building secondary payloads for future Diwata 3. We also are into capacity building such that we can have a laboratory where we can develop these payloads. We will produce highly trained personnel in designing, developing, and testing payloads. And of course, sharing, we are to share the knowledge that we gain. So we set out to develop not one, not two, but three optical payloads. We aimed for two spaceborne payload, aimed to be able to fit it into a Diwata class satellite. It's a 50-kilogram satellite, our Diwata 1 and 2. The dimension of Diwata 2 is 50 cm by 50 cm by 50 cm, and its weight is 50 kilograms. Now, we also aim to develop another optical payload, but this time for a drone. So it will be an airborne payload. Now, why is that so? Why did we go for three? First of all, for the Diwata or spaceborne payloads, we learned that the Diwata satellite returns back to the Philippines, approximately same site, every 30 days. So, for example, the satellite rotates around the Earth, but then returns to the same spot after 30 days. What can you use it for? What are the things that you can look at after 30 days that would make sense if you look at it after 30 days? So we thought about agricultural monitoring, because plants, they grow slowly, so 30 days or 1 month would be a good time to monitor the progress of the crops. If that were so, we thought, okay, how can we test? So if we are developing cameras, how can we test them if they're working well? So we have to have another camera that we can test right away and even use right away. That's why we opted to also develop a camera that can be fitted into a drone so that we can launch it and send it in fieldwork. By the way, we don't have a Diwata 3 yet. So hopefully it's in the future. Okay. So the thing is, there seem to be nobody in the Philippines who knows optomechanical design. Here at the University of the Philippines, there are many optical physicists. We know our optics. However, optical design is an engineering field. But I looked everywhere in different universities, nobody is doing optomechanical design. And so me and my team had to learn optomechanical design. So the first thing we did was I looked for professional courses that taught the following. So I found from SPIE that they teach optical system design, practical optical systems, optomechanical, lens design, and aberration theory. And I had me and my team learn these online. Okay. And immediately we used the things we learned in these online professional classes for our project. So again, I said we built 3 cameras. So here's the first camera. We nicknamed it PAN for a panchromatic camera. It's the first spaceborne payload. What we did was we used the same sensor that was used in Diwata 2B in its enhanced resolution camera. Here's a picture of Diwata 2, which is still flying in space. It has several cameras, and one of them is the enhanced resolution camera. Inside it is this CCD. It's a black and white or panchromatic CCD. And we wanted to use this because it already has space heritage, meaning it has been tried and tested in space. So we're sure it's going to work in space. Okay. However, our contribution would be to design and build the imaging lens and the housing. And remember, we have to look for local partners that can help us build this camera. Fortunately, as part of the project, we had to go around the Philippines looking at companies that do these kinds of work. And we found this company, PIMES. And do you know that this company, they're actually the ones that build the projectors, the lenses for brand name DSLR cameras, projectors for, again, brand name projectors, etc. They can do their precision optomechanics. So we gave them our design. Of course, all these designs that we did were torture tested in silico, meaning we have software to test our design for tolerance, etc. And we gave these designs to our first industry partner, PIMS. And here are some action shots of us testing in their lab. So roughly, this is how the panchromatic camera looks. So essentially, this is the one we built. This is the imaging lens and the casing and all the optomechanical parts that will attach it to the chassis of the satellite. Because this is a spaceborne camera, one of the important things that you need to do is to test it for a space environment. So in the middle of the pandemic, we had to bring this to Japan. In Hokkaido University, they have the Space Mission Center, and they also have the replica of Diwata 2, the engineering model of Diwata 2. So this is the underside of the Diwata 2. So here is where the panchromatic camera is. This is the primary payload for now, but this is the underside. We brought it to Japan for thermal vacuum test. This is a huge chamber. It can be filled with nitrogen to make it very, very cool, as cold as the environment and space, and it can be heated for when the satellite is between the Earth and the sun. So the satellite is in front of the Earth and it's being hit by the sun, so it can get hot. And also it's being cooled for when the satellite is behind the Earth and the Earth is between the sun and the satellite. So it needs to be torture tested this way because remember, satellites go around the Earth and they cycle through very hot and very cold temperatures. So here's a close-up look of the back of the panchromatic integrated to the chassis of the satellite. And I'm pleased to say that it passed this space environment testing. These are the researchers from the optical lab who went to Hokkaido University Space Mission Center in April 2022, in the midst of the pandemic. They had to test for COVID throughout the trip 6 times, going into Japan and coming out of Japan. The second spaceborne payload that we developed is a line scan camera, and we nicknamed it Malikmata. But this is a multispectral camera. It has 3 sensors, one for red, green, blue. You remember your printers, your all-in-one printers, diba they have a scanner where you can put your document, colored pictures, etc., and you can scan them. The sensor there is a line array, a line camera, just like this. That's the same sensor there. It has red, green, and blue filters. There are actually 3 line sensors there, one for the red, green, and blue. And what we did was we will use this for a push broom space camera. So if panchromatic was a single shot camera, which is black and white, this would be a push broom multispectral camera. We also found an analog front end chip. So by the way, this has no space heritage yet. Okay? But this time, the imaging lens was COTS, or that's short for commercial off the shelf. So if in the panchromatic camera, we developed the lens, in this case, we bought a lens, an imaging lens. Whereas here we developed the sensor, and because this is a line scanning camera, firmware needed to be developed so that we can stitch the image, just like what Dr. Rollan earlier discussed. So this is an exploded view of the Malikmata. So again, this is a commercial camera. You can see the brand even. And again, we developed the optomechanical chassis and the sensor there. And initially, we tested it in the lab if it can image. So this is just a picture projected on a screen, and we had Malikmata capture the image. And this is the rendered image. So this is RGB. So each line that it gets actually is producing a colored pixel, but you have to stitch each line. So here's the rendered, or rather the colored image based off on this scene. And then we all again found local partners to help us test and create control boards and firmware, and even do thermal testing. So here's a DOST agency that can do the testing. As you notice, everybody here is wearing masks because again, we were doing this project in the midst of the pandemic. And so shout out to all the industry partners that worked during the pandemic. Now, lastly, let me talk about the hyperspectral camera that we developed for a drone. So this is our airborne payload, and we nicknamed it Hype. So similar to what Dr. Rollan discussed, the idea of creating a hyperspectral image is that you have a lens here, and this is the important optical element. This is called a dispersing element. This one is, if you look inside, it's called the PGP, or sometimes it's called um, GPG. But essentially, what it does is it has a prism. We know a prism disperses light into a rainbow, but another dispersing element is diffraction grating. So a grating is a film with several very fine lines. And the interference of light, when it passes through these fine lines, cause the light to split into various wavelengths. So imagine you have a dispersing element, which is a slit, diffraction grating, sorry, then the prism, which further disperses it, then another diffraction grating. So you can have 3 times dispersion. So this dispersing element already comes with a foil, which has a thin slit. And again, a camera is attached to the end. So between the lens and the camera is the dispersing element. And so as we scan, for example, the direction of the scanning is along the X. The image from the camera that we see is image of a spectral line. Okay? And we have to scan to create the hyperspectral data cube. Initially, we prototyped this using a rail. Sorry, this is a motorized rail, precision rail. So we can attach this. You can see here the prototype, the lens, and the camera, and then we scan this, and you can see here the video of the hyperspectral image as the scanning platform, or rather the camera, goes across the rail. Okay, then we can render. Remember, please, that, for example, this is the wavelength axis. Along here is the wavelength axis. The image, or rather the spectral, rather the wavelength can be rendered into color. If you, for example, use the RGB channels or the spectral sensitivity of a certain camera, you know, it's RGB spectral sensitivity, you can convert any wavelength into RGB, or digital number in R, G, and B, and then you can render it. Okay. So here's another way of showing it. This time we're showing it in terms of rendered wavelength. Okay. And what's important to note here is that the scanning speed matters, because you can either have an extended or a squished image. By the way, in these images here, you see the actual rendered colored image from the hyperspectral image cube. We have rendered already the color from the spectrum. So we were able to build that, and we were able to attach it to a drone. This drone is massive. It's the Matrice 600 DJI. It can carry a payload of up to 8 kilograms. Right? So this is the rendered CAD image, and this is the actual image in the field, picture in the field. Here's a CAD 3D model of our hyperspect or HIP, the hyperspectral imaging camera. We can attach a GoPro also for taking a look at where it looks. Okay? And everything inside, including the software for stitching the image, was all developed by the team. So for example, here's some stitch picture using drone camera. And the idea was, since we are looking at agricultural monitoring, sorry about the line there, but the thing is we will follow this flight path. Okay. So here's a already color rendered hyperspectral image of the scene that there was this first pass of the drone. We noticed that there were some lines here which seemed to be periodic. So we figured out, okay, there's something with the swaying of the drone, perhaps. There seemed to be some vibration along the the scan direction. And so the team figured it out. By the way, here's a lawnmower type of stitching for the whole scene. In the background is a Google satellite imagery of the same scene. So we've geo-referenced it as well. So you can see the uh, dirt roads the roads line up, the trees seem to line up as well. Okay. Okay. And the team figured out how to improve the stitching, and this is the latest improved version. Again, it's already rendered in digital color. It's also geo-referenced and overlaid in Google Earth. So this is a hyperspectral image, but rendered in digital color. So while we were doing this, we needed some tools, and there were no tools available, so we had to develop our own tools. For example, if you were to have a scanning imagery and you can't fly it yet because it's still in prototype or development phase, what do you do? And we're in the middle of the pandemic, so we've developed a rotating mirror. So for example, here's a camera with a slit or dispersing elements. So what we can do is, here's the rotating mirror. Instead of moving the camera in scanning mode, it's the mirror that we rotate to be able to scan the scene. Okay. Here's another way of testing a line array camera this time. So remember Malikmata, it has a line array camera. So instead of it moving, we instead moved the scene. So we projected an image which is scrolling downward. So the image that projects on it is essentially opposite of when you have a camera which is scanning over a fixed scene. So in this case, because we have a projector, we can move the scene across a scan path. And it seems like the line array is scanning over the scene. We also have developed a sort of satellite uh, uh, platform simulator, or some gantry crane that we can attach our cameras on so that we can simulate movement. Like for example, here's the gantry crane that we developed, and here's Hype, and we're making it move across the gantry crane. And here's the rendered hyperspectral image from that satellite scanning simulator, or the gantry crane. So we laid out on the floor several checkerboard patterns, Macbeth color charts and other charts, and even colored monitor with images there, etc. And then we had the satellite simulator carry the payload. Okay, so this is fine and good, but I think I would like to emphasize that beyond the technology that was developed by this project, the most important output, I think, would be the highly trained personnel. Technology can come and go, technology can become obsolete, but the training these people obtained working together. So we have geodetic engineers, we have physicists, we have mechanical engineers, we have electronic engineers, and the experience of working together to achieve an objective which is highly technical, and precision and tolerance requirements are so high, and making them work together and making it work, that experience of making something complicated together is, I think, the most important output of this project. We have trained several engineers to do so. So that ends my presentation. If you have any questions, you can screenshot this my contact information. Okay, thank you very much.
Thank you very much, Doc Jing, for taking us through Hype. I'm really, really happy how the Philippines is now progressing, as we already can create our own payloads, and who knows, maybe in the future, what more we can create as a nation. And I'm very sure that all of us are very curious and have many questions for Doc Jing. Again, if you have any questions for Doc Jing and her presentation, please use the chat to type it in and we'll deliver it on your behalf. Let us now proceed to our question and answer portion. May we ask our presenters, Doc Jing and Dr. Therese, to open their cameras. I think, Keith, you can join me in reading some of the questions.
Right. So we have multiple questions in our recent chat box now, but we're going to take some time to go through all these questions. But I'm going to start with Dr. Therese. We have a question from our team in PhilSA from Kara Patricia Canlas. Apart from balloons, what are other platforms that are suitable for high altitude pseudo satellites?
Hello, good afternoon. Thank you for that question. So not only balloons, you can actually use so we have there are companies that have this what they call this I'll just describe how it looks. So they have this like longitudinal structure with like it's like a plane that's just a skeleton. It's like you have this way and then perpendicular to it, and then there's a company in New Zealand where you can mount that structure on a car, and then it just drives builds up this momentum and velocity, and then it launches. It's like when you have this folded paper plane. So that's another example of that. Yeah.
There's a follow-up here. Is it like a glider?
Oh yeah, I've been finding the right term. Yep. Thanks for that.
Yeah, okay. Thank you. I think we have another question actually for Dr. Therese. Would the training goal be to no longer have human monitoring? Or will there be still some human evaluation after the machine has finished inputting all of the data points? So this question is through our YouTube, asked by Kofi.
Thank you for that question. Is it in the context of like using the data or operational? Maybe I can just answer both. So for operational, it's also like you have a space mission or space launched imaging payload. You also have this monitoring team, but maybe fewer people, and you monitor the weather condition, and you monitor whether it's already going to your target location. And in terms of application, so you still have to do post-processing, similar to what Dr. Soriano mentioned about teaching as well for drones. So yeah, it's kind of mix of drone and spaceborne.
Thank you for that, Dr. Therese. We also have actual questions for Dr. Jing, Dr. Soriano. Aside from the thermal vacuum testing of the camera payload, I think this is for Hype. Did you also perform vibration testing?
Yes, we did vibration testing for the panchromatic camera. Actually, the only test that we weren't able to do, not for Hype, by the way, but for the panchromatic camera, the only, because of time constraints, the only space environment test that we were not able to do on the panchromatic camera was the radiation test. Because outside the Earth's atmosphere, there would be lots of radiation from the sun that can damage the digital electronics of the camera. The vibration test is very interesting because we found a local partner who can do vibration tests. Okay, so they were all, the experience was interesting because this company had been doing it for example, automotive industries. So they have a vibration platform. What is done is you feed the vibration profile of, say, the launch rocket. Okay, so these things have been measured already. So you feed that frequency profile, and the table will shake with the same vibration as the rocket that will launch the satellite. So it's important. The vibration test is very important for spaceborne cameras because they need to survive the launch to space. If their screws and the optics crack or the mechanical parts loosen up, that's a big disaster. So you have to test first on Earth if they can survive the launch to space, and that's the purpose of the vibration testing. And I'm very pleased to say that the panchromatic camera survived that vibration testing alone. So here locally, we tested it by itself, standalone. So the panchromatic camera was shook, okay, and it survived. It still worked, and then we attached it to the Diwata chassis, the bus, and then shook the whole satellite with the camera in, and it still worked. So I'm very pleased that it survived the vibration test inside the satellite.
That's very insightful, Doc Jing. We're glad that the payloads are still working after that test. We also have another question for Doc Jing in our MS Teams from from Mr. Christian Anthony, I think. The question is, what method do you use to regulate the temperature of the image sensors whilst in space? And is there a need for a special component for this?
You would want to reduce the power usage in when you're in a satellite. So there are passive cooling solutions while in space. So for example, cooling the engineers in field cell know this, but other cooling solutions could be, for example, there's a the heat can spread through the area in the satellite. By the way, the satellite itself covers the or reduces the heat directly on the camera. Okay, but a passive solution would be that you have fins or metal plates that would dissipate the heat away from the camera. That's why we have the chassis. As you notice, the chassis is a metal. But for the high P, being flown by the drone itself, there's artificial wind. So there's enough cooling inside the chassis of the hyperspectral camera as it is being flown by the drone.
I think that's great, and it also gives us a peep on like all the processes in creating not just the payload but also the platform, the bus of a satellite, and lots of testing to be done. Thank you so much for that, Doc Jing. Now we have questions again for Dr. Therese. How do you handle noise in your captured images, such as thin clouds, thick clouds, haze, perhaps cloud shadows, etc.? This question is from Mr. Ronnie Pagia from MS Teams.
Thank you for your question. Good question, actually. It's also the one of the most challenging because we don't really launch the balloons when it's really cloudy. Haze, there are still some areas with haze, and we can't really avoid them. So for now, since we're on the development stage of the hardware, we're just stitching as much images as we can, but later on we're already I think one of the teams that's doing the machine learning are developing algorithms where you can just feed your own sets of data depending on your sensors as well, and then they'll give you a model for your particular sensor. So it's mostly for like machine learning approaches. Sorry.
Thank you for that. Keith, do you have any other questions for Dr. Therese?
Actually, we have another question from Mr. Ronnie Pagi again. Out of curiosity, how many payloads have you lost, if you have any? And in your experience, how far away was the payload when you retrieved it?
Good question. How many? I think we already had 4 launches, 4 or 5 launches, and fortunately we haven't lost. It's just that it took us like one whole day to find the balloon, and it's near. I'm not sure if it's near the river. So all of the payload so far was recovered, but there was a flight wherein we're already going to the boundary towards the boundary, which is I don't know what's going to happen because it you have this permit, right, where you launch and where you can only launch, and beyond that you don't have a permit. So yeah.
Thank you for that, Dr. Therese. How about Doc Jing? Do you have some experiences about when developing payloads where, some payloads were destroyed or lost, so you have to recreate it?
Fortunately, not in this project, but in other projects involving a camera, I've already lost. But that was for underwater use. So yeah, we've lost several cameras under the sea, but not fortunately not for spaceborne or airborne. Airborne, not yet. Yeah,
Okay, that's
hopefully
very
not.
fortunate.
Knock on wood. Yeah.
Yeah. Okay. How about okay? So we have a okay.
Speaking of water, we have a question actually from about water quality processing. This question is from our very own ESSMSD, senior research. Senior SRS, Jennifer Demaligaya. Her question is, for water quality processing, I am curious how you will do atmospheric correction since the balloon is changing in altitude while capturing images. I think she's referring to Dr. Rollan for this question.
Thank you. So atmospheric correction. Yeah, we're considering applying atmospheric correction. So it will be, yes, it will vary because the altitude is changing. But so in terms of current development, we are looking at flying a different balloon, which is bigger, significantly bigger. So with that balloon, it will remember the trajectory goes up like this, and then it will burst and goes down. But this one with bigger balloon, you have a float altitude. So you have uh, specific range of altitude, and then we're focusing on that range of altitude, which is not too varying. So then you can apply a more uniform atmospheric correction. But we haven't tried that. We're not yet in that the phase of development.
I think that's very great. So I think now we're entering the remote sensing side. This question is for Doc Jing. How about for infrared and near infrared spectrum for the camera to get more detailed information about plant health, etc., etc.? So this question is from Sergio and Andres Jr. from Microsoft Teams.
Well, actually, the hyperspectral camera can reach up to 1,000 nanometers. We can actually detect up to one. The sensor is a CMOS, so the sensitivity of the CMOS camera tapers off at 1,000. So if there are signatures, at least uh, between 800 or 700 to 1,000, that's important for crops. We can do that. As for infrared sensors, you might need a SWIR. That's kind of expensive, and you also need cameras that are also sensitive up to say 2,500 nanometers. So they are also expensive. So I think we can do it, except that it would be for another project.
Thank you for that, Dr. Jing. Actually, we also have another question for you. This is from Mr. J. Sim Sokobos. His question is, what effects do radiation, temperature changes, and orbital dynamics have on the functionality and durability of the panchromatic cameras in space?
So again, the radiation, let me start with the radiation. Radiation from the sun can actually flip the bits on the digital electronics. So the switches on the camera are very important. You know, just say, for example, we have to control it. We just say that this bit must be turned on so that the camera can be ordered to capture an image. But for example, if there's radiation from the sun that causes the bits to flip, then instead of doing the procedure, it will not. So radiation testing is important to see how durable how durable the electronics is in the camera. For the case of the what was again the thermal
The orbital
the
dynamics,
what was this? I think he asked
temperature
23.
changes, and orbital
Right.
dynamics.
So temperature change, as I said, it should survive a lifetime of going back and forth from say -10 degrees to +50 degrees within a very short span of time. So that cycling of -10 to +50, -10 to +50 can easily wreck an ordinary camera or ordinary device. But you have to design your camera to survive that kind of frequent, or rather that lifetime of thermal cycling. So that's it. That's the important thing. Then we test it. Of course, all things will eventually get destroyed. So all the things have a lifetime. So the satellites, their payloads also, their lifetimes are estimated. Right? Orbital dynamics, by the way, depends on the satellite. But in our case, Diwata 2 does not have any thrusters to keep it steady in its altitude. So eventually, because of friction with some small air molecules, thin air molecules out there, it will eventually lose altitude and it will eventually crash to Earth. You might be aware that already Diwata 1 has already graduated, meaning it has already gone back to Earth because of that. So it's not a problem of the camera, it's a problem of the payload, or rather the platform, if it can still go on and on. Okay? So for that, you need, say, for example, thrusters to keep it at a good altitude.
Thank you so much for that, Doc Jing. I think we're going back again to Dr. Therese. There are actually also a lot of interesting questions here for Dr. Therese. I'll read one of them. This one's from John Carlo Aporbo. Seeing the erratic movement of the balloon, how extensive is mosaicing these images and how long would it take? So I think this refers to perhaps the bundle block adjustment and maybe also aerotriangulation to add GCPs.
Thank you. Yeah, it is really, really challenging. Remember, I'm the only one who's mainly focusing on data processing. There, I get some help, yep. But yeah, it's really different because as you can see, if you remember the footprints that I showed you, wherein you have this like really I don't know, like stretch or distorted images. So with the first launch that we had to filter based on the Euler angles or the pitch, roll, and yaw angles. You filter out those that were almost looking at the horizon. You just retain only those almost pointing nadir. So we tried, but if you started with a very distorted image and stitched them together with erroneous image, then you'll produce all the way just propagating errors. So you retain first the acceptable range of images and then you just process them. We're also using similar to drone like Python open drone map. You can use that.
Actually, this is also interesting for us, and also another from our audience. Actually, we actually have the same question as this one. Dr. Therese, what software do you use to stitch the spatial images and in image processing?
So we just use Python packages because we really have to be able to customize the processing. But So we have two stages, right? We have onboard processing and we have post processing. So for the onboard, you can just actually look up, for example, what the mobile devices use to stitch panorama, right? Because we're only using Raspberry Pis, which are very limited as compared to your laptop capacity of computing. So you can use those readily available. We only use all free open source software, actually. OpenCV, computer vision related software.
Thank you very much for that, Dr. Therese. Now we have questions again for Doc Jing. I think this is more on the project management side. So hello, Dr. Jing. This is again
Yes.
from Ronnie Pagia. How does your team address the skill shortage, if any, considering the high technicalities needed for the project?
If you remember that slide which shows the capacity building objectives, the thing is we have to share the knowledge. So we built several modules from our experience, the testing techniques that need to be done, and the because we learned okay, if you now have this camera, how do you test it? So we tried to learn and applied it. So we build several modules on how this can be done. So we can share this. By the way, the some of the project personnel got hired by PhilSA. Some are still there, and they're working in PhilSA right now. So and that's a thing. Sharing, or rather participating in this kind of webinar is one way of sharing the knowledge as well. But the modules that we prepared can be shared eventually to other schools that need to learn the techniques that we learn.
Thank you very much for that, Dr. Jing. And I really agree with her answer. I was actually also once, just like all of you there, just watching these videos, and now I'm very happy to also be working along these colleagues of mine here at PhilSA. I think we have other questions.
Actually, this is a follow up with Mr. Jason from Sir Ronnie. The question is also for Doc Jane. What challenges does your projects encounter during development? And since part of the project is to train personnels, what are the plans for these personnels? Are they still working in the project or other satellite projects, or has been absorbed by PhilSA? Actually, I think Doc Jane already answered this, but maybe you can also elaborate or add more
Yeah, so
for this. Yeah.
yeah, as I said, okay, so personally, I think the most important output of any project are the people. Okay, people. Technology can easily be made obsolete. So again, I said the people are some are got absorbed in PhilSA. Some stayed for a while and then transferred to other companies. What was the first part of the question?
What are other more challenges aside from having high technicalities on the project?
Well, in particular for this project, it was done during the pandemic. So mobility was a problem, but we managed through online. A lot of development actually occurs first in silico. You do not have a prototype. You do not make a prototype until you're absolutely sure from simulations that they will work. So there was a lot of going back and forth on the design in silico, meaning simulations upon simulations and then testing. Okay, what if we use this other design? So the challenge was, fortunately, we were still at that phase at the peak of the pandemic. And when by July 2021, companies started opening up. By then, we have had 1 or nearly 2 years of perfecting the design in silico or through simulations. So that was the challenge. The because it happened during the pandemic. That was it. But maybe we could have done more or finished earlier or did not extend if we did not have any pandemic. we had to extend the project actually because of the limitations.
Thank you for that, Dr. J. I think personally as well, before PhilSA, I had an experience where a project actually started in the middle of the pandemic. So I really understand how it is difficult to even operate in such a difficult manner and, do it face to face while we, the nature of the project is to actually be together in one place to operate and to build these systems for the sensors. So Dom, are there any more questions for both Dr. Therese and Doc Jane?
I think we still have a few more minutes, like 2 more minutes for questions. Of course, we want to really entertain and make the most out of learning from our very esteemed guest speakers for this event. For Dr. Therese, um, what image corrections or enhancements do you usually do after capturing images and before processing the image? Is it very similar to satellite imagery, or what is the difference from using balloons and also other devices as platforms?
Thank you. I think the main problem with um, when stitching the actual spectral images are the gaps. And filling that gaps, we just initially tried the uh, convolution, wherein you apply statistical kernels, but we're looking into applying, actually, because we're improving the system, the objective is to avoid those gaps already. So you don't really have to apply those image enhancements because you don't really wanna you wanna avoid changing an actual value, right? Just implying from your surrounding pixel. You want to have the actual measurement. So in the future, we will be having very minimal image enhancement, just those that are really unavoidable gaps. So yeah, maybe more just rely on the convolution, not really the AI. We don't really need that kind of enhancement.
Thank you for that, Dr. Therese. Actually, I have a personal question for this. Is your sensor up for commercialization in the future? I think most of us actually in the audience as well are very interested if are there any plans for, for commercial use for the sensor itself?
Thank you. Yeah, actually, so we're looking at other companies like collaborations. So we collaborate with balloon companies. So for example, if you are a balloon company and of course when you have when you have that kind of platform, the main application is for Earth observation, right? So those companies are looking for cameras that can be used for lots of applications, and the hyperspectral imaging payload is the best kind of payload for that. So I think, yeah. So yeah, to answer your question, yes, can be commercialized.
Okay, thank you very much for these questions. Actually, we have one question from Miss Annie Lean Arias, but I think this one, I would just be answering this question. What's the mission purpose of Mula satellite to be launched on 2025? So I think this is more of a PhilSA related question. So I'll just answer this. So Mula means multispectral unit for land assessment. And currently, we've sent already 16 of our PhilSA engineers, some of who are my close friends, to create this satellite. And the applications are for disaster management, land use and land cover change mapping, crop monitoring, and forest management. I think in the chat box, you're going to see some of our teammates sending the link to the AVP to know more about Mula. And we also hope for you to learn more about PhilSA at our social media pages and our website at philsa.gov.ph to know more about the events and updates about space, satellites, and also the agency.
All right. Thank you for that, Dom. First and foremost, thank you for all the questions. I think from all of us, we thank Dr. Therese and Dr. Jing for answering all the questions. And personally, for me, a woman in science, it's very difficult to be in. We would just like to appreciate Dr. Jing and Dr. Therese for their contributions for science. So now, before we go, may we ask for a photo opportunity with Dr. Therese and Dr. Jing? Is our ready?
Is the SIICaP team ready? Okay.
Okay.
Let's have a short photo opportunity.
Let's hold our smiles. Like everyone is still trying to open their cameras. All right. Let's take our photo in 3, 2, 1. Are we good? Captain? I think. All right. Okay.
Okay. To our audience also, we would like to thank you everyone for your participation and thank you for all of your questions. I hope you learned a lot from this afternoon session. Once again, thank you again very much to our two speakers, Dr. Therese and Dr. Jing. And I think
Thank
I
you
want
for
everyone
having
to,
us.
yes, I
Thank you for
think that
having
would be
us.
great. Yes. We want everyone to also join us in the next sessions, and we will also have other guest speakers like Dr. Jing and Dr. Therese who will also tell us more about space, the space related endeavors, and also how we could use more about these space data. I think that ends our presentations for today. And to conclude our webinar, let us hear from Engineer Cyrus Nicopante, the team leader of the SIICaP project, to give his closing remarks.
Hi everyone. So rinig naman ako. Okay. So good afternoon everyone. I would like to thank our participants from various sectors. So we have been conducting SIICaP for 2 years now and have seen it evolve. Just last year, we were able to reach participants from 73 provinces of the country. Another one is the increasing participants from our national agencies and local government units. I hope this webinar has enriched you with yet another space technology. Sa mga nakaraang webinars na pag-usapan na natin ang space launches, Earth observation applications, and many other more. Also, this webinar has informed us with another area na pwede natin salihan, especially to our students who are maybe not yet decided on what area they want to pursue. I want to thank our speakers today for their invaluable contributions and sharing it with us here. My actual first job before joining PhilSA was operationalizing the data processing and distribution of Diwata to images. I was in the software side of things, so I'm actually happy to meet Dr. Therese, who also happens to do the same with the development of data cube from their pseudo satellite hyperspectral imager. Nakaka-inspire and really happy to know people working on the same area. I also thank Dr. Jing. So she was our program leader in Stamina for Space program. So may TED Talk siya sa YouTube. So in her TED Talk, one of the things she emphasized was that we have local problems sa country natin and it needs local solutions. So meaning tayo rin in the end makaka-solve ng problema ng bansa. So sa presentation niya makikita natin na pwede tayo makagawa ng sarili nating tools and apply them locally. And she's doing what she actually preaches. So again, thank you, Dr. Therese and Doc Jing for accepting our invitation and spending time and effort with us to share your knowledge with this area. There were a lot of questions today. I apologize for the lack of time. We can accommodate them. However, we have recorded those questions and we'll try what we can do with them. So if our speakers allow, we will send the answers back to you. So I guess that's it. I invite everyone to follow Phil's social media pages to know more about our programs and enjoy the rest of the day. Thank you.
All right. Thank you, Sir Nico, for the closing remarks. Before we send the evaluation link, may we ask our audience for a photo opportunity with you. So please turn on your cameras if possible and hold your smiles for a few seconds as our SIICaP team takes screenshots. All right. So I think everyone is trying to open their cameras as well. Okay. Oh, ang dami natin. Wow. We have around 200 participants in our MS team, so we have a lot. Okay. So right now our team is actually trying to capture every slide or every part of the. So please hold your smiles. And 3, 2, 1, smile. Ayan, wala mo nang sasalita. Let's all hold our smiles. Okay, that's 2. Three. We have 3 screenshots right now. 4. All right. I think, okay, we've managed to get everyone else cramped up in the picture. All right. So that ends our webinar today. For our participants, please complete the evaluation form to receive your certificate of attendance. The link is posted in the chat box. So if any one of you can see it, it's already in our MS Teams in this meeting. And yeah, so thank you for joining the mission. Please continue following the PhilSA journey. Visit our website and follow our social media for updates. Have a good day, everyone.